to other experiments. The first question you might ask is, why is there so much stuff in here? For that, the reason is, well, there's an experiment under development. Once we get data, once you're in full analysis mode, this will be burned down to the things that you actually want to do physics with. But right now, we want to save everything. The other question you might wonder is, why is this all just plain old numbers? In fact, this data format is called POD.io, where POD stands for plain old data. It's a deliberate choice over something more powerful, like you could imagine a track object that then points to its parents and has methods inside that you can transform it with and what have you. There's three main reasons why we decided for this flat format. One is performance. This is become an LHC experience, but also informed by AML and what have you. These long vectors of just plain floats or doubles are just much more performant, especially on a GPU or other like accelerator hardware. Second, this way you can use it without loading any libraries. If you usually use experimental data, that comes with its own root libraries that you have to use in order to get anything out of it. Here, I can do this straight up for my own roots. This is not in fact the C shell container. And you see these warnings for no dictionary. It doesn't matter. You can work with it anyway because it's just plain old data. So the third reason is hard-learned experience from even Hera days, like from the turn of the century. Because when we try to reanalyze data from back then, we ran into a whole bunch of problems. This is self-explanatory. It's wordy, but it's self-explanatory. You know what you're getting yourself into. That's just all I wanted you to say on that aspect, because it might confuse you if you're used to star root, fun for all, alley root, or whatever they're called. Okay, let's get back to our example from yesterday. And I'm going to do this slightly differently than the tutorial write-up. The code in the write-up is perfectly fine. I just want to show some different ways of going about it. First things first. You see here this if statement that is a cut on whether the particle is finally stable. You might want to make more than this cut. You might want to cut on PT, on phi, on eta, and what have you. And every time you do this, you get another indentation level. And another if here, another if here, another if here. This is essentially how this code is written here. See, ding, 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 ding. Instead, what we're going to do, or what I'm going to do here, is replace this with what's called return early pattern. So instead of opening this if clause and then another one, we just deny this if clause. If the particle status is not what we want, we just continue. We break out of the loop already. And now we know it is a final state particle and we can continue. We could also add another one, and we will later. But what all this does is really just decrease the number of unnecessary if statement or long if statements and parentheses. Okay, so what we did yesterday was essentially just getting momenta. So we have reconstructed particles and their status, and we have empty particles and their status. There's a bit more we want to do now, because first of all, we want also the particle ID. Cool, easy enough. See if it fills it for me automatically. No, it doesn't. Okay. What's important though is now that we want to make a comparison between the thrown particles and the reconstructed particles. That's not straightforward. It's not the same length, so it's not clear. So what happens instead is that association makers keep track of that. So there are two arrays, one that tells this simulated particle belongs to that reconstructed track, and another one that tells you that reconstructed track belongs to this simulated particle. It's just index numbers, actually. So first of all, we need to get those. And then we will have to work with it. First, what do we want to get out of this? We're no longer really interested in this momentum, but we can keep it if we want to. What we really want is the eta distribution, or the T distribution, or what have you, about the particles that have not been reconstructed or the ones that have been reconstructed, and maybe the difference in their resolution, by their point. So let's first decide what we want to save. Whoop. We want the eta. We want the eta of the matched particles. Same thing as yesterday. It has a name that should be identical to this, and it has a title. This gets displayed atop of the plot. And if you then have something behind it with a semicolon, this is the x-axis. And you could continue like this with the y-axis. And then 100 bins going from -5 to 5 because we have pretty good acceptance. Though -5 to 5 is maybe a little bit optimistic. And for the ones that do match, we also want to know how far away are we in phi squared plus eta squared. So R. Title, name title, in this case 5,000 bins, because we probably want to zoom in quite a bit because I don't think we're going to see, hopefully not going to see more than 5. Okay, and then comes again our actual event loop. First thing we want to do is we want to focus only on charged particles. So for our final state particle, we now take its PDG code, and specifically that absolute part of the PDG code, because we want to have both particles and antiparticles. And then we can check. Excellent suggestion. I love code titles so much. So we want to keep ions, muons, kaons, protons? Yeah, protons. Good guess. What would you guess next? Do you have another guess?
This is AI coding.
Yes.
Wow.
Oh,
Learned this from you, or it learned this in you? Did it learn this from you specifically or in general?
in general. I don't train this. Taking it from essentially worldwide code.
Really?
Yeah.
Wow.
Okay, so now we made sure that this is, but that logic is not right. And you know, quite want to do that. So now we're gonna build, we're gonna access what this actual, yes.
Where do you find PDG codes, just in general? Like, how do you know, like, 321 for, you know?
If you're in this field for more than a year, then you have these memorized by heart. But they are essentially, PDG stands for particle data group.
Yeah.
They have a list of all of these particles, which is
Okay.
it's
yeah,
super
well,
long. It has all kinds of
It
entries.
is long, yeah. Okay.
There are usually some shorter summaries about like these typical stable particles.
Yeah, I found some article that, but it only has like the standard model
Mhm.
elementary particles, doesn't have any, like a proton or something.
If you want to be part of the club, you can write to the PDG and they will send you the particle data, the PDG booklet, which is revised about every year or so. Then you have a little lookup book for all kinds of particle properties.
If you're trying to find the actual codes, just Google search PDG codes, and there's a PDF that comes up basically right away that has a full list, and it includes any stable particle, not just quarks and gluons and stuff. I clicked the result before and the one after it. Thank you. I'll send the link. No, I have it.
So now we can build the truth. Now we can access the truth particle formation. We're going to use a T vector 3, which is a root object that gives us access to things like pseudo rapidity, phi, and all of that stuff out of the typical Cartesian properties. And yes, first we save this. AI was a bit faster than I was. And skip the step of saving it by itself. And now comes the tricky part. Now we want to find out what reconstructed particle corresponds to, if there is one, corresponds to this truth particle. So there's a list of indices corresponding to all of these, called SIMU ASOC. Well, can all be great names. Stop cheating. But yeah, in principle, this is it. Finds if there is something associated with it. Ah, not quite right. Because what we need to do is use this. The RICO associate that corresponds to this SIMU ASOC is the one that we're looking for. You cancel it like this and just repeat this twice or 3 times. I would probably just pull it out right now and make it more clear. And now we can build T vector 3 again. Yes. Questions so far? Here's another thing that AI did better than the example code, because T vectors automatically have a built-in function that determines delta R. It's also, the main problem is, if you look at this code where it's originally done, is this line. It takes the delta phi difference just by subtracting the two numbers. But what if you have something that is close to minus pi and something that's close to pi? They're very close to each other, but the difference will be huge. And delta phi, delta r, and so on, they automatically adjust this for you by adding 2 pi as long as it's necessary. Question. Why do we want to fill the true eta? We have a matched particle. Why do we want to fill here at the true eta? What is the purpose of this particular histogram? No, it's just efficiency. What we're trying to do here is efficiency. We want to see how often do we catch a particle and how often don't we catch it. So if we know the truth, then yes, at this true eta, we found a particle. We don't record at this point in time what that eta is or what it was reconstructed at. We just want to see the efficiency at that eta point in the histogram. How it deviates is here. What we could also do is we could have a two-dimensional histogram and have the truth and the reconstructed eta on the two axes, and you get hopefully something that looks somewhat diagonal and probably somewhat fuzzy. And I think probably it's done here. This feels that. All we need to do is scroll. No, we don't need to write it. Write it. Let's see if this works out of the box. By the way, here is the problem if you trust AI too much. This is what the AI wanted to do. What we instead need to do is this. It is called a stochastic parrot for a reason.
Stochastic parrot, I like that.
So let's look at these two instruments. First things to observe, the name is the name that we gave it in the definition. It has at the y-axis the thing that we put at the first semicolon, at the x-axis, and at the y-axis it has counts. So this is the truth, all strong charged particles, and this is how they are reconstructed. First thing to observe, the shapes are slightly different. and the number of entries is different. So we had 5,000 particles in total in this particular file. Only 3,500 of those were reconstructed. And you see, this is a particularly good area because lots of them are reconstructed as opposed to what's strong. And here at the end, we lose quite a bit. One thing we're gonna do next is just divide these ones by each other, and you will find that that is your efficiency essentially. And then this is the delta R between. Remember, we're between 0 and 5, but we took a bunch of bins. That's specifically so that we can zoom in and see what this really looks like. And that is pretty good. So once we reconstruct them, we do so rather well. We may want to again set a Y scale, set a log scale, and set. Okay, before continuing, let's see. Can everybody produce these plots? Can anybody produce these plots at this point in time? Oh, okay, all right. Good. Nice. So, where are people stuck? Let me ask that. Show me here. Trying to compile this. That's not how it's going to. You want to execute it with root and the macro. Where are you?
I'm installing the squads.
Okay. How's it looking for you? Mhm.
I don't know. So it takes me 5 seconds, which is what? Something takes me 5 seconds, I'm looking up, so I'm just trying to help.
Just exit the C shell. Start it again.
If you look at the game Y axis, everything capitalized.
Get the axis. Yeah, that's weird.
There you go.
I don't like that.
Sure, restart the kernel. Why not?
Yeah, I really don't like that because everything else is. My virtual box breaks, so I'm falling. Turned it on today and it's saying that I can't find the operating system. I don't know. Wait, I thought you did it already.
That was through an e-browser. I'm gonna actually code it.
What? The audit, yeah. Well, really funny how every audit thing ever has. You can do exactly what you want, but then it's like show this on the screen is somehow like difficult.
Let's add the efficiency, why not?
Yeah, what?
What's going on?
Oh,
Yeah, because it goes.
Thanks. Golden rule in programming. Ignore everything but the first error. Because everything cascades from there. So you always go to the top of the error messages, start there. This is line 38.
These two.
but like 0 to 1.
Yeah.
What?
Can you?
Ah,
Same thing.
very, very,
I
very
think it's better just popping on the same thing.
brackets.
Yeah, but it's not. But mine.
Okay, I'll do it. You put the windows on top of each other, you just keep shift tab, alt tabbing.
People the.
Yeah.
Yeah,
the access.
range.
Here, it doesn't matter where you put brackets. This is how the other author decided to do it. But the indentation matters quite a bit because you really want to, well, it doesn't, in Python, it matters for the code. In C++, it's just for visibility.
Oh. Yeah.
That was great.
So you see now that this bracket closes that, it's a mismatch. See they're red.
Wait. Right. The hell?
If statement.
Okay.
Close the for statement. They'll have one missing. Is that for statement?
Well, you thought. Don't think it works. Okay, so which one's on? I think this one.
Try again.
No, track.
No,
Match. No, wait.
but no.
Yeah,
Oh, it's.
you're not wanting it. Oh, okay, no, that,
Yeah.
I thought, okay,
Yes.
I didn't even see that line over the one. That's almost exactly the same. Just drag them on top. No, like, if you put it on the right half of the screen, then it automatically makes it the same size. Yeah, we do that. No. Damn it. It's not exactly the same. Is it difficult? My problems like C++ is so much typing. If you make the font that doesn't ratio.
I saw one. Uh. Yeah. Try to- I was gonna put. Oh, that's. Operations.
This is in the same place, or are you editing it different?
Okay, I mean.
Yep. And there needs to be a closing reference. So, because they're all done.
Wait, no, that's more meta.
Yeah.
We don't want them.
I mean, yeah.
Dude, just do the same thing with the AI. I'm a T1. Well, just do a ratio. That's basically just the ratio minus one. That's exactly the ratio.
Yeah.
Essentially, you have to chase down one more missing bracket or bracket.
Uh,
Are you guys holding up?
I just. Holding the, even if the deep is
Mhm.
segmentation.
Ah,
Right.
uh, segmentation violation typically means. Yeah.
I went on the yard in St. Valley. But it's. Just one of them has. Little statistics, right? It's-
You have the,
Why they moved, they didn't.
no, you have the.
Yeah, that's like if we were able to find it in the track.
Yeah.
Yeah, so.
The same numbers.
If you identify everything. It's just, the second one is just, it's not first one, but do we have a track associated with this? Yeah. Yeah.
Sorry, right here.
Yeah, it should be, I would just, it looked like it was exactly the same, that's why I was excited.
Yeah.
I thought like the, it equals -2 regions was on lockdown, but.
Try to comment out the loop lines. Okay. That way. So if you,
And then the next step anyways, if I match on the two of them.
then you can at least isolate that that's happening. Okay. And do some see outs type things.
Okay.
How's it looking here? So it works for all of us, all of you?
No,
No problem. All right.
well, I don't have this file. So I can't,
Which file?
the one that,
Oh, you're fine.
Oh.
Now make a third one of the ratio.
I'm sorry.
Oh, you know, it'd be really cool if the ratio's in the middle.
Yeah, but I don't know. if it is.
One.
Oh. Tells you.
So that's why I don't think it was space on.
Can we go to yours?
I don't know, Siri, can you go to mine?
Sorry?
Are we stuck on yours number?
Yeah.
Can't. Oh,
Fine.
fine.
Yeah, the calls and
Yeah.
relative
Oh, yeah.
I think I don't have my data on.
You can
open it, you know,
maybe can.
Sorry?
Maybe can.
Oh, yeah, August 2003.
Yeah. The developer whose name is Renee run been answering for like 30 years, and you can just tell that she's getting everybody's shit.
Much faster solution.
You just get more and more sassy.
So the file lives on your home computer, on your actual computer.
Discussions. I don't like it. This is literally just a vector.
Well, I mean, you don't need to copy it over.
Right.
Okay.
I account computer.
Yeah. So.
No, the file I made is on.
Oh,
I can't get it.
I'll make sure.
Your account.
Just what is, what?
Oh,
Just.
Just, you seem to know about this, but they're like,
Just like.
they have a bunch of stuff.
Yes.
I don't know how to work on.
Like, we're not entirely sure what it is, like, there's two things, two coastal pentacords. Which you go through like the.
Can you help?
Yes,
I can send.
Have been identified.
Me by WhatsApp, whatever, and not.
X, whatever, like, all the particles that it's like.
And I go.
Sorry.
Like X and then.
Oh, the restaurant. Yeah, yeah. This is the green tea.
I mean,
Oh, okay. And we're gonna meet what?
who was talking about this?
2025.
Okay, sorry.
Okay.
Yeah.
Okay. So aim to be there 5:45. Cool. Do you mind if I invite? Yeah, he's here over in Vietnam. He's giving a plenary talk, probably about now, the user meeting. Yeah, that'd be great.
It's complaining about.
The speaker's phone is ringing or somebody's? Somebody's phone. Oh, it's mine. Jerks brought their phone to my lecture. Oh, I'm the jerk. It's me.
Oh.
Yeah, that would be great. Thank you.
But you gotta change the scale to not.
Oh, sure. Yes. Yeah, John is cool. I usually talk to him on Google. Yeah,
Okay.
I have some questions at his end as they finish up the session, but if he's free, it'd be great to. Yeah, thank you.
When I look at, I'd like to say two more things. Remember, we wanted to write this and then it displays empty because it drops all of these objects from memory.
Subtract one.
So the trick to do is to essentially draw a clone over copy.
Subtract one.
Oh.
Like, just go from -1 to.
Oh, well, that didn't work. So the right one.
Yeah.
And it's matrix.
Okay, doesn't want to do it. Yeah. Okay, one more thing. Let's make this an efficiency. How would you go about that? Divide the bound by the original. Well, how do you divide a histogram?
Yeah, using the divide function.
Exactly. Yes. But first, let's not destroy our original information. So
Create a new histogram.
I cannot find 2000. Oh,
you clone it and then let's see. Yes. Correctly, yes.
Nobody knows what these are. Are they, well, I mean, what, like, we don't know exactly yet,
Oh, I don't know.
like, are, like,
Yeah. Okay.
is there a
Yeah.
code?
I really don't.
Translation.
Because there seems to be code for like, there's two pennant organs.
And you see our efficiency here. I mean, this is
Last time what we did was.
very low statistics. That's why there's a holes in there. But you see, we're sitting pretty much at one here in the backward region, losing a lot here in the far forward region. And other than that, on the order of 90%, that's not bad at all.
And then we'll donate all this stuff. I want to show you.
This isn't like a exhaustive list of codes. Because there's like the very rare, like. Very rare particles, like I have no idea what this thing is. Okay.
For your homework, I suggest following the rest here, doing the resolution analysis. But for now, I would like to make sure that everybody gets this going.
Particles that you use in simulation, like Monte Carlo particles.
Okay, all right.
I would also like to point out two more things in this tutorial. If you haven't scrolled down yet. There's a Python version. For people who are familiar with PyRoot or with Uproot or Python, go ahead and take a look at that. It's in the process of being Pythonic, more Pythonized because it's a straightforward C++ translation and doesn't really take advantage of Python's capabilities, but it works. And the same exercise is essentially completely repeated here in Python. There's one more thing, and this I recommend all of you to at least consider. Root is moving away from the T trees. It's trying to replace these with our data frames. Those are more space efficient, faster, annoying, terrible. But if you get into the habit of right now, while you're still learning, to try and use our data frames as much as possible, then maybe you will end up unlike us grumpy people and don't find it.
I take offense though, I'm not grumpy at all.
So the our data frame version it reads completely differently. I'm not going to walk you through it now. It's just would confuse things more than it would help. But I really encourage you to take a look at this and see if that's something that you can wrap your mind around. There are also more clickable links in this write-up. And there is an entire section of solutions, not just solutions, but also other helpers. One thing you might want to do, some people like to prefer this, and I usually do this once I get to my analysis in a bigger stage, or if you only want to use some parts of root and mostly have a real normal C++ program, we have a skeleton analysis that provides you with a CMake lists, with an example how to just compile straight up against root. The code itself is ridiculous. It just says hello root, and that's it. Or it will also maybe fill a histogram randomly and then exit. So the code would be replaced with what you're actually doing, but it will give you an option of compiling your code, which is the second version. You can also do this root and add a plus at the end. That's not something I recommend. At the point where you are wanting to compile for real. Use an int main and this CMake. Yes.
Stupid question,
No such.
does PyRoot have data frames?
Yes, I believe so. Okay, instead of going through more code, I think I'll open the floor for questions and otherwise continue walking around until I see plots on everybody's computer.
Open the plot.
Nice.
So okay, just have it.
Can you make an efficiency plot of that?
Why is it bigger than one?
No, you just need to divide one histogram by the other.
Scale like this one. Zero and then one. Negative axis, logarithm. Like, it's like a log scale. But both ways away from zero.
Yeah.
So, does it look extensive or what?
Log, so if you have zero in the middle of your plot,
Oh,
you have a log scale going up and a log scale going down.
what is the log of a negative number?
The log of negative y underneath. Like it would be like mirrored from the top. So you're zoomed in at zero, and then the further away you go. it's zoomed in.
Oh, that's some
I guess
craftsmanship.
You
Possible.
you could just custom define it. Yeah, you define a log. You define a log scale, you reverse it, multiply everything by -1, and then you append it to the original log scale.
Yeah, that's essentially what you would create a new histogram.
Can I change this name to be there or?
You can probably just clone that histogram and then find out plot options on how to invert the scale or downward. And then you need to play around quite a bit in order to match them.
So they have
This
to,
playing around is a pain.
if I commit, is it just gonna push it, or is it gonna create a pull request? Okay, you want to do this one? Thank you. There's a typo. It says input.
No,
Here it says in the final. Here it says input final.
I don't understand one thing. I told him he got the plots. I told him like send analysis code. I tried running it, but in my case it's showing the empty canvas.
Show me the,
So I do have to install like a local desktop as well.
Ah.
Like the shell. Oh, the code? Yes. Oh, yeah, I think you.
Have you ever seen that? It's called a bend error.
you need to get the input file as well.
I do have the input file. That's what I was checking.
Just lives in a different,
The input file.
Yes, but that's it.
I renamed it. It's in the same directory, so I don't think I. But it's okay.
it's not looking. Looking for this file.
Yeah, oh, I'm ready. I.
highlight.
No worries.
Wait, see info about.
When I find the number.
So.
What's the JDAT mesh for?
It's very nice.
If you bend the error bars so that you see them better, if you draw several things on the same plot. It's not like your error bar is sideways.
This is what.
It's like if you plot, if you have a lot of information on your screen.
Okay, so about what time?
Which error bar,
Okay,
so see with this.
I'm asking-
Move them out of the way a little bit, so that you can actually see what's going on.
I thought they were trying to draw a square bar into the third dimension.
I don't know, I thought they were trying to do the 2D ones.
are you able to change that?
It's it's the first time I've ever seen a
Okay,
something like that.
You know, yeah, that was a lifesaver, so, yeah, because, okay, okay. And I carbon copied you on the note. And if you want to flip burgers, that'd be great, I'd love to have you.
Yeah.
Does that work?
I mean, those bands make sense.
My life.
Okay,
That curve
yep,
thing.
could
I
be
don't
raining,
understand.
go for it, so,
Okay, which
okay.
And this,
Yeah.
That's for if you have, it says it's for if you have a lot of information on your screen and you have a lot of points close to each other and you have error bars on everything, you might not be able to tell which error bar was at which point, so you just put one like this.
Okay.
So you can tell, I've never seen it in my life, but
You leave
Funny.
at 8, go to the city, and we'll be done by
That's how
then.
you copy.
And you're driving to the city?
it's not easy to like
And you're taking the sedan?
change something small, run it.
So I'll keep the van.
Takes a few seconds,
I
right?
think there's one inspection.
Like, no, if you're just messing with a plot and you're going back and forth, like generating it, changing little things, generating.
So, I mean, you can also do it and also make changes here like I did before.
If you want,
Okay.
Yes, it is a.
You're gonna-
Five.
default is Matplotlib.
It's set up so.
Oh.
I mean, we do have,
Five.
I used to use Root all the time.
Means
but-
it's six.
I'm just trying to.
Right, bye.
No, because this is just like. List the points, graph it,
Yeah.
title, like this is just like exactly what Matplotlib does. Oh, if you want subplots, you just say divide.
Yeah, that's what
Okay. That's easier than Matplotlib. Some problem? No, I was just wondering where this.
Extension, the plus is Root's version of compiling it for you. And it creates a dictionary and all kinds of stuff. For some reason, and I can't put my finger on why, but for some macros, it's necessary to compile. It's usually a giveaway when the output starts with the include files, because those are only needed for compiling. It shouldn't hurt, but can I see the error message? Yes, it's the log. The log, I believe. Maybe not. No, for the failed. Literary choice box. Yeah, it needs extra libraries because to understand this. Can't really get into it because it needs to create a dictionary for these particular classes, which we use, which Root doesn't know by heart. Once you compile it, it looks for those and creates the right classes. But yeah, that's kind of like log file. That's the problem.
10 megabytes.
Yeah. By the way, it literally works very well. I open like a gigabyte size error messages with that, and it's fast. Yes, loads all of it into the buffer, and if you have like 4 gigabytes of buffer, you really get into trouble with the RAM.
I know.
Whereas literally, if you
I
just
know exactly
show you
what
where
code
you
this is.
I've actually been very,
Looking at it and I don't understand.
I think being in kind of the dull roar situation.
Already
To being in a coffee shop.
No, it's essentially, people are free to go. I just wanted to make sure that, nice, this works.